Okay, all right, moving on to the next page. We've got a bicycle tire with an internal volume of 1.52 liters, contains 0.406 moles of air, and that we're told the tire will burst if the pressure reaches 7.25 atmospheres. And what we want to figure out is to what temperature in degrees Celsius does the air in the tire need to be heated to cause a blowout. So we've got volume, we've got moles or N, and we've got the pressure that we would need to get to. That means we can calculate T using the ideal gas law. So if we start with PV equals nRT, we just want to move N and R over to the left side of the equation here, and we'll have an equation that we could solve for T. So PV over N times R will equal the temperature. So all of these look like they're in the right units here to match with R as well, liters, atmospheres, moles. So let's just plug all this in. The pressure is 7.25 atmospheres. The volume 1.52 liters. Number of moles 0.406 moles. And R, of course, is 0.0821 liter atmospheres per Kelvin mole. And everything's going to cancel out there except the, let's see, liters cancels, atmospheres cancels, moles cancels, the kelvins, and that'll end up back on top. So this would be the Kelvin temperature of the that we would need to get the tire to. Now that means we'll have to change it to Celsius since that's what the problem asks for, but we've got to get it in Kelvin first. So punch that in, and it looks like 3 significant figures here, so let me round this to 331 Kelvin. Now when we go from Celsius to Kelvin, we're adding 273. So if we're going to go from Kelvin to Celsius, we just need to subtract 273. And that would be 57 degrees Celsius here for that tire to burst. So that is pretty hot for kind of environment outside, but that's not out of the question. Maybe in a garage, the sun beating on it, possibly. Okay, next question. And I can tell this is going to be a good one because it's pretty big. When in danger, bombardier beetles can fire a hot, toxic mixture of chemicals at their attacker. This mixture contains quinone, compound that is formed by the reaction of hydroquinone with hydrogen peroxide. We're given the overall equation there, right? Fairly complicated. But then we're given a bank of known reactions. So this looks like Hess's law. We're going to try to combine the known equations to generate the equation there for the target reaction. Okay, so we're just going to put the pieces together. So let's see. Let me start with the reactant here, C6H4, 2 hydroxides. That's right there. And that's perfect. It's 1 mole. It's on the reactant side. So let's start with that equation. C6H4, 2 hydroxides, aqueous is going to go to C6H4O2 and some hydrogen gas. And that one was aqueous. Now, let me underline here. That is in my target reaction. That's also in my target reaction. That's one of the products that I want in my target reaction. Hydrogen is not, so we'll have to account for that as we go along. Didn't have to change that reaction at all, so we don't have to change the enthalpy. So plus 177.4 for that one. Okay, the next thing we want in our target reaction up here, we got this guy too, is H2O2, which is hydrogen peroxide. That's in the second equation here in the bank of known equations, but we're going to have to reverse this equation. It's a reactant up here, so we're going to want it to be a reactant down here in our Hess's law evaluation. So if I reverse this equation, right, that would become a decomposition. The hydrogen peroxide is decomposing into hydrogen and oxygen gas. And if up here that is an exothermic reaction, down here it will be endothermic. So I'll make that a positive value for the enthalpy because that's the way I wrote the reaction down here. Put an underline under H2O2 because that is in my target. Now the other thing in my target is 2 moles of water, and I haven't introduced that yet, so I'll have to try to get that in my next step. So I want some water, and I want liquid water. So here's liquid water down here in this last reaction. So if I take that reaction and I double it to give me 2 moles of liquid water as a product, that will work. So 2 moles of water in the gas phase, converting to 2 moles of water in the liquid phase, and that would mean I need to double the enthalpy there. So that'll be 2 times minus 43.8, right? But I didn't have to reverse that equation, so that one would stay negative. And that gives me the 2 moles of water that I need, 2 moles of water in my product. So I've got all the pieces that are in my target. I just need to make sure everything else is going to cancel out and or disappear when I add these together. So I'm going to have to account for 2 moles of gas phase water, 2 moles of hydrogen, and a mole of oxygen. Well, that looks like this reaction right here. And this reaction looks like it's set up correctly to cancel out the things I want to cancel out. So far, I have hydrogen as a product. Here's hydrogen as a reactant. Oxygen as a product. Here's oxygen as a reactant. Water as a reactant. Here it is as a product, right? So it's just a question of getting enough. So I do need to double everything that's in the equation in the bank. So I want it to be 2 moles of hydrogen gas, a full mole of oxygen gas instead of a half, makes 2 moles of water in the gas phase. And that means I want to double that reaction. So 2 times minus 241.8 for that one. And now let's see how all this works out. 2 moles of hydrogen here is going to cancel with the 2 different moles I had on the product side. 2 moles here on the reactant side of water will cancel with the other 2 moles of water in the gas phase on the product side. So that might be a little tricky if it's there as gas and a liquid. Be careful of that. Phases are important here. 1 mole of O2 is reactant, 1 mole of O2 is a product. So if I cancel everything else out, all that's left is the target reaction. And I forgot plus the hydrogen peroxide there, plus 2 waters in the liquid phase. So Hess's law says if I add all the pieces and get the reaction I'm looking for, I can add all the enthalpies and get the enthalpy I'm looking for. So we just need to combine this together. Now watch your signs, right? Watch those negatives there, and don't forget your multiplies. So 177.4 plus 191.2 minus 43.8 minus 43.8 minus 241.8 minus 241.8. And this all comes out to minus 202.6 kilojoules would be the enthalpy for the overall reaction. So that's delta H for the reaction here. And that makes sense. It's exothermic, right? And the beetles are using this to drive off the attackers. So that energy that's released by the exothermic reaction will go to heating this mixture, this kind of soup of stuff that the beetle is shooting at the thing trying to attack it or eat it. So helpful that that's an exothermic reaction, helps make it warm there. Okay, let's see if we can, well, you know what, there's 1 page left. I think we can fit both of those neatly into one video without having to make this one overly long. So we'll stop there. Should be able to wrap this up with one more video for that last page.